Okay, so our final lesson in our unit on light, or the wave nature of light, is lesson number 6, and it's about diffraction. And Francesco Grimaldi was the one that first coined the term diffraction, as it referred to basically the bending of light around edges. And there's a very small but very important difference between interference and diffraction. Interference is defined as basically the superposition effect originating from two or more discrete sources of waves. Diffraction, though, refers to the interference effects that originate from a single source or a single wave front because of the bending of light. Okay, and so we know that waves can bend around objects when their wavelengths are comparable in size to those objects, right? This is the reason why sound waves, basically, if I'm in my classroom and I'm speaking, someone that's down the hall can hear me. It's because the sound waves come out of the door and they bend around that barrier and kind of propagate up and down the hallway. So waves can bend around objects. And when monochromatic light shines through a single slit, which has a size close to the wavelength of light, you will see an interference pattern. And that interference pattern is not unlike what we saw yesterday, but is a little bit different. And so, of course, just an aside here, if Thomas Young used only one source in his experiment, why is Thomas Young's source an example of interference and not diffraction? Because he only had one source. Well, the answer to that is quite simply that he used a single source, but he shone it through two slits. And so two slits is basically just like having two sources, and those two sources interfered. Anyways, diffraction, and what diffraction is all about, is basically we've got a plane wave that comes through an opening with some width. This then, the light bends through around basically the edges, and we end up seeing this really nice diffraction pattern where we have this central maximum and we've got all these bright bands that extend all the way out. A few observations before we go into some of the formalism. In diffraction, the central maximum has a width that is double the width of any other maximum. Away from the center, right? So here, of course, this is not equally spaced, but away from the center, all of these bands are equally spaced. And the intensity decreases as you get farther and farther away from the central maximum. So in diffraction with a single slit, you will see one very bright central band, and then you will see equally spaced secondary bands that spread farther and farther out. So this is basically the diffraction pattern and how it looks a little bit different. Now, there's two different types of diffraction. We're not going to talk about them for very long, but Fraunhofer diffraction and Fresnel diffraction. Fraunhofer diffraction is basically when the screen is very far away from the slit. Okay, so the rays that are hitting the screen are effectively parallel, and that gives a diffraction pattern, of course. Fresnel diffraction is when the screen is close to the slit, and so the curvature of the wave fronts becomes significant. And this is generally how we treat things. This is just more for interest's sake at this point, as we're studying this, because what we're going to do is we're basically going to treat this as being the general case, and this is in general what we're looking at. So some formalism. The single slit equations, or the diffraction equations, we looked at Thomas Young's interference equations, and now we're going to find the single slit equations. So in a very similar setup to what we had before, except now we have one opening. We have a single slit, and we have a top ray that emanates from, say, up here, and a bottom ray that emanates from, say, down here, and a middle ray. And they all combine and meet at this point P1. And we're going to select theta so that the top ray is exactly one wavelength longer than the bottom ray. Okay? So we're selecting theta such that we're imposing this. The top ray is constructively interfering with the bottom ray. All right. When the top ray and the middle ray meet, they cancel each other out. So because these would be destructively interfering, so the top and the middle cancel each other out. Same for the middle and the bottom. The path difference then, in either case, is lambda by 2. Right? So we've got lambda between the top and the bottom, but between the top and the middle, or the middle and the bottom, we've got lambda by 2. And that's the net effect for destructive interference. Okay. So that means that sine theta is equal to lambda over W, or W sine theta is equal to lambda. So this is how we get this first equation. Unfortunately, however, what we've just stumbled upon is a condition for destructive interference where we've got an integer number of wavelengths. And so what we get is we get almost the opposite to what we had with interference. All right. So theta 1 was basically the angle for a 1 lambda path difference. Theta 2 would be the angle for a 2 lambda path difference. In general, for destructive interference, we've got the slit width times sine of theta is equal to m lambda. And that's for destructive interference, which is a little bit different than what we had before. Because here we have W sine theta is equal to m plus a half lambda, which would be the condition for constructive interference. The equation looks very, very similar to what it looked like in the previous case, but here we've of course flipped our definitions for m, which now applies to the destructive case, and m plus a half, which applies to the constructive case. So it's reversed, so be very careful about this. All right, here's our next example. Again, looks very, very similar. We've got a slit of width W, a certain distance L to the screen. We've got our bright spot, and then this is our central maximum. But then here we have all of our dark spots, because remember the dark spots are now being labeled m equals 1, m equals 2, m equals 3. And so we have some distance x2 to the, this would be to the second dark spot. The distance between the middle of the central maximum and each of the dark fringes is xm. And so for destructive interference, we have m lambda equals wxm over L. And for constructive interference, again, it's reversed. We have m plus a half lambda equals wxm over L. And this would be the case for constructive interference. So let's take a look at a an example here. We've got a slit with a width of 2.0 times 10 to the minus 5. We're shining red light onto it, 620 nanometers. At what angle does the third order maximum occur? What we need to do is we need to unpack this. This is diffraction, because we're talking about a single slit. So we're going to choose our proper equation for diffraction. We're talking about a third order maximum. Because this is diffraction, and we're talking about constructive interference, we use a slightly different formula. M is still equal to 3, but we need to now use the formula for constructive interference in a diffraction pattern, so we have the m plus a half lambda, and that's equal to w sine theta. We sub in our numbers, and we get that angle as being equal to 6.2 degrees. Okay, so again, we need to unpack what the question's asking before we get there. Here's the next slide, the next example, example number 2, which is a single slit that has a width of 9.5 times 10 to the minus 6. We're illuminating it with monochromatic light. Lambda equals 640 nanometers. The screen is 1.3 meters away. I want to find the distance from the center of the pattern to the first order minimum. So what we have here, here's our screen, and basically here's the center of the pattern, and this would be the big central maximum, the big central. I want to find the distance from here, the center, to the first dark spot. So I know what the width is, I know what lambda is, I know what L is, I'm trying to find X. This is destructive interference because I'm asking for a minimum, and I say m lambda, because this is the condition for destructive interference when we're talking about diffraction, is equal to Wxm over L. I sub in the numbers, and I get 8.8 times 10 to the minus 2. Okay, so about 8.8 centimeters. And in part B, it says find the width of the central maximum. Well, if I found the distance from the center of it to the edge of it on this side, then the width of the central maximum is simply 2 times this distance that I just found. And I get 2 times 8.8 times 10 to the minus 2, which is 17.6 centimeters. That is, in a nutshell, how we solve diffraction patterns. Again, the derivation is presented mainly for a background and kind of where things come from. We need to know how to use the equations. That's what's more important. The last little bit here is an interesting little point. It's called the Rayleigh criterion. And a little bit of a different topic, and certainly not enough for one lesson on its own, but the Rayleigh criterion is really what describes the fact that when 2 point sources are far away from you, they appear as one object. And until they start getting closer and closer, your eye can't decipher. So a car on a highway coming towards you, that's very far away, can appear to be a motorcycle until it gets close enough that you can distinguish between the 2 point sources of light, the 2 headlights. And basically, the 2 images become resolvable by your eye when the central maximum of one image lies on the first order maximum of the second image. And that's called the Rayleigh criterion. So the angle at which that occurs, he worked out as 1.22 lambda over d, where d is the diameter of a circular aperture, and theta r is the minimum angle between any 2 objects. So really, your eye is a circular aperture, and this has applications in human optics. So when you look out and you see these 2 headlights coming, the diameter of your pupil, the circular aperture, and basically the minimum angle from where you are to these 2 objects will basically tell you whether or not you're going to be able to see either one image or 2 images.